Good afternoon, everyone. I'm waiting for a good afternoon back.
Good afternoon.
Hi.
Hi. Good to see you all again. Let's see, I want this one on here. Yeah. Are you ready for the next lecture? We're diving deep into the ANOVA, this block, into the analysis of variance, and we're continuing with this today. And actually, after today, I think we'll be done with ANOVAs for now, because we're gonna cover basically all the variants of the ANOVA that you need for, well, most experimental designs that you can that you will be performing during your studies at our department. So today we're going to dive into the repeated measures ANOVA, and we're going to combine this at the end with the mixed design ANOVAs. And there were some questions I saw about the I think it was the ANOVA, to which extent you needed to know the formulas. And I want to emphasize this again also for this lecture, because if you read the book, if you read Field, then you will see that in some chapters he is very explicit about how to calculate sums of squares, for that matter. And he will give you a lot of information on how to actually proceed in this. But for some chapters he doesn't, and one of those chapters is the ANOVA, which goes into the mostly conceptual part of it. And when we go into the mixed designs and the factorial repeated ANOVAs, the same holds in those chapters. So you can use Field and the book, the chapters, as a guide to know how much detail you have to apply to actually be able to calculate the sums of squares. So for today, for example, the relatively easy part in explaining variance is done within the one-way repeated measures ANOVA. So we'll be looking into that. We'll be diving into this so that you have a conceptual understanding of what is going on here and which parts of the variance are actually going to be explained. As where we go into the mixed designs and the factorial repeated ANOVA, we'll skip that part during the lecture, but also Field doesn't cover those topics. So it's more about your conceptual understanding of the designs and what it's doing, and then being able to apply those techniques for your own research. Okay, so for today we have we will mainly be focusing on the repeated parts, and explicitly the one-way repeated ANOVA. And we've seen the term one-way before, so is anyone able to tell me what this refers to again? What does the one-way mean?
That there's one independent variable.
Yes, that there's exactly only one independent variable. It can have many levels, but there's only one. So what was the term that you used if you had more than one independent variable? For example,
Factorial?
Factorial, that's right. So the terminology that is used in Field and that we use also in the lectures, you can deduce what kind of design you have by knowing what one-way / factorial refers to. But in this case, we also are combining those. So we already covered the one-way independent ANOVA, and now we're at the one-way repeated measures ANOVA. So we're still having only one independent variable, but in this case it's repeated over time. So I think I've mentioned this before, but it's also good to, I'll just mention it again, it's also good to have a bit of a notion on what the data looks like in SPSS. So for example, if we have a one-way independent ANOVA, you have a column with the dependent variable, which contains all the values of the thing you're actually trying to measure. And you have a column for the independent variable, which holds your categories. So it's not just knowing what is the one-way ANOVA and what does independent mean, but also trying to think of how that looks, what that looks like in as a data structure. So, for example, if you look at this one, the one-way repeated measures ANOVA, are you able to visualize in your head what this looks like in SPSS? I hope by the end of this this lecture you can, and if you can already, then that's only great. Okay, here we go. So one dependent variable which is continuous, it's the outcome variable. We have one independent variable with two or more levels or categories. And the one thing that makes this repeated is the fact that we only measure within the same subject. So in terms of experimental design, you could have your participants show up, establish a baseline on, let's say, for example, assertiveness, and then you provide some training on assertiveness, and you have a follow-up measurement where you establish again what their level of assertiveness is, and that's repeated measures. We've seen such designs already with what test again? We've seen this one more time. Which one was that? Anyone? Where you could have a baseline and then a follow-up measurement.
The repeated sample t-test?
Exactly. We've done this exactly with the repeated sample t-test. But now with the repeated ANOVA, we are able to add more repeated measures, because the repeated measures t-test was restricted by the fact that you could only have two levels of your independent variable. But now we can say, well, let's also do a follow-up study. So we want to have our baseline, our treatment, and then measure again if the treatment actually raised the levels, and then after a month, let's see if it still stays high, or after 2 months. So you could have follow-up measurements, so you could follow people over time. So you can have different, more than 2 levels in your design. But the categories are assigned within the individual. Does that make sense? Is that clear? Can you already imagine what the data looks like in SPSS?
No.
Not yet. Okay, we'll be looking into that, because it's a little bit of a strange thing going on compared to what happens when we do an independent ANOVA. But we'll look into that. Instead of a t-test. Oh, so the question, if you have only two levels, if it's to use a ANOVA or a t-test, it doesn't matter. It should yield the same kinds of results. So that's not a problem. Okay, before we dive into the actual data and the example, it is good to first stand still for a moment to think about the assumptions, because essentially they are the same as we had with the independent ANOVAs that we've did so far, but it has to be how do you say that, calculated in a different way, because where we had, for example, the assumption of equality of variance within the ANOVA, that the variance of the different groups that you have should be equal, assuming that your null is true and you sample from the same distribution. In this case, you don't have different samples because you measure within the participant multiple times. So there are some deviations from this. When you deviate from some of these assumptions, then you are able within SPSS to run some multivariate alternative analysis, and SPSS will provide you with these results. And we'll look into this also. So you have some options to choose from when interpreting your results. So of course you have your normality. So the first one, of course, is the, as I stated, the univariate or multivariate test to perform. We're actually interested in the univariate test, but if you have some violations of assumptions, then you could opt for the multivariate analysis of this same results. The dependent variable, again, must be continuous, and the normality distribution should hold, again, for the separate variables that you are interested in. And here comes the deviation, that we are still interested in equality of variance within the groups, but this time we measure that with the Mauchly's test of sphericity. And that's a very difficult word, meaning just equality of variance. Where we, with the independent samples, could easily look at the variance within one group and compare it to the other group. What happens with repeated measures is that the variance of differences between groups are measured. So if you have level 1, 2, and 3, then the difference between level 1 and 2 will result in a new vector, and you can look at the variance within that vector. And you can compare it to the difference between level 1 and 3, for example, or to level 3 and 2. So if you do all the comparisons of the differences between the levels, that is the thing that is actually measured within the Mauchly's test of sphericity. We're going to look into these assumptions as we will be doing our analysis after the break within SPSS. So we'll come back to this.
I'm sorry, can I ask a question?
Of course.
You just explained that it was the variance in the differences between the groups.
Mm-hmm.
Why does it say variance within groups on the slide?
Yeah, so it tries to approximate the variance within the groups by looking at the differences. So it wants to, the Mauchly's test of sphericity actually wants to say something about this, but is still looking to see if there's internal consistency within the individual. So, and I think it's also referenced in the chapter in field that it's in general terms told that we want equality of variance, but what's actually happening behind the scenes is looking at the equality of the differences between these.
Mm.
So does that make sense?
I think it's gonna make sense after I read field.
Okay, very good. Okay, well, this one is a bit hard because, and I've added this one because there's if you read the chapter in field on this topic, then it has a lot of, well, how do you say, a sort of a decision tree when you should opt for multivariate results, or when you look at the corrected test statistics. And well, when reading the chapter myself in the book, I thought it was a bit hard to follow what the decision tree actually was. So I've put it down here for you. So we're going to look at this for a second. So if we're, I want to see it all. Is this readable to you?
Yeah, it is.
Yes.
Okay. So the first thing is essentially a test of a Mauchly's test of sphericity, where the same kind of test holds as what we've done with the Levine's test, meaning that if it's not significant, then there isn't a difference in variance, and then it's okay. So if you have a p-value from this test which is larger than 0.05, then you can just look at the sphericity assumed results of your analysis, and then you're done. That's okay. But if it's not, then there are a few steps that you have to go through to determine what you should actually do. And these are, well, I think a bit complex. So the first one is that you look at the epsilon value. And again, we will be looking at this when we actually do our analysis. And if this epsilon value is smaller than 0.7, then yeah, there's a lot of ifs and elses. Then if the sample size is larger than the amount of levels that you have plus 10, if that is true, then you can look at the multivariate results. And if it's not, then you can go opt for the Greenhouse-Kaiser correction. And if you go the other route, where this is actually the value of this epsilon value is higher than 0.7, then you can go directly for the Greenhouse-Kaiser correction. And if this value is lower than 0.75, then you apply this correction, and otherwise you will have to apply the Heinfeld correction. So what I've done is I've added a few numbers in front of these decisions. So this is 1, 2, 3, 4, 5, 6, and 7. And I've also added the reference to field for these decisions, so you can look up in field how field explains all these steps for these decisions to try to make it a bit more clear for you. So, well, this is relevant when you actually doing research and you want to apply this analysis, and you have some violations of equality or variance, so you can follow these steps. I won't ask you to memorize this by heart. So I will not ask you exam questions to tell me if there's a significant difference in the repeated measures ANOVA, where you have to go through this whole tree process to find out what is the correct value. If I want to know something about the tree process, I'll ask you directly, but I will not phrase it in that way where it's dependent. Your correct answer is dependent on knowing this by heart. So rest assured that I won't do that. Again, we will relate to this when we're actually doing the analysis in SPSS. But for now, I just wanted to clarify, to tell you how to interpret this this tree structure, and where you can find the references, so at least you have a map on what to apply and when. Okay?
Excuse me, can I ask a question?
Of course.
Will we have to be able to do the corrections ourselves as well?
In what sense?
So if the assumptions are violated,
Mhm.
will we, for example, be asked to perform a greenhouse geyser correction?
Okay, so these greenhouse geyser corrections are all provided by SPSS.
Oh,
So it just gives you everything, and based on the tree structure, it's up to you to decide which results to look at in SPSS.
okay, thank you.
Yeah. Okay, you're welcome. So going back to the slides, yeah, here we go. So when we're doing repeated measures, it means that we're measuring people at multiple time points. So where you previously would have one score per person, now you can have multiple scores per person. And that means that in terms of explaining variance, where we previously only had the variance within the group, where we could say that if you're in this group, then we can compare your personal score to the group mean and look at all the deviations from the group mean to the total mean as an explained part, and that part that is off, that's not correctly on target, we could determine as the unexplained part, and we would be done. This doesn't really hold for repeated measures, because the thing with repeated measures is because you measure individuals multiple times, you also have an within person variance component. So if I would run the 100-meter dash a few times, then I wouldn't put down the same exact score, the same exact times for each time I run the 100 meters. I would vary. Some would be a bit faster, some would be a bit slower, and for all the times I try, I will have some average, so I can essentially define my personal deviation from my own personal average within that. So by correcting for your within person variation, you can essentially reduce the amount of error that you have in your model. So you're actually dissecting the variance components, not just between the groups, but you're also dissecting components that are within the individual. And if you have those components, then you could, in that sense, reduce the error term. And if you reduce the error term, just like we've seen with the ANOVA and with the factorial ANOVA, if we reduce the error term, then we have a higher signal to noise ratio, because the amount of error that we have is smaller, even if the amount of signal that we have for one specific model that we're interested stays the same. And that is essentially what we're seeing here. So the thing that we're interested is the model. So essentially differences between the groups and the amount of variance that is explained within for these groups. But what we're also seeing is that the mean squares of the error that we use here, so this is the error, and we see there that the error is determined by the variations that we have within each individual, subtracted by the sums of squares of the model. So we're correcting the error term for the variations that we see within. But we're going to run through all these steps step by step, and let's see. There are a few terms and terminologies that are used here. We have K, of course, again for the amount of categories within the group. We have the N for the sample size, and we have capital N for the total sample size, which is explained here. So my example that I'll be using here is we're going to look at the amount of car accidents in a driving simulator that our participants have when we apply no alcohol, when we apply a little bit of alcohol, and we apply a lot of alcohol. So we have 3 levels of alcohol. Let's call it drug use or whatever. These are the levels within our independent variable. And the thing that we will be measuring is the average amount of car accidents that they have within our driving simulator. So the data looks like this. So, and what we have here is, of course, our participants, and each row represents an individual. With this individual coming back to run the experiment 3 times. So let's, for example, say that in the first week we've put him or her in the driving simulator and looked at the amount of accidents. Then a week later, the participant can come back. We will provide some alcohol, and in the final week, a week later, we will provide a lot of alcohol and see how much accidents the person has in the driving simulator. So for each individual, you have them run through all these 3 steps, which would essentially say and that's the thing where what I mentioned with the way the data looks in SPSS, it's a bit different than when we had the independent variables group, because there we could assign a column to the independent variable which would have the categories assigned to them, so you know which individual is assigned to what group. So if I were to ask you to look at this and tell me where do I find the independent variable here in my data?
Independent variable is the columns. So each column represents one of the levels.
So that's a very good observation, that the column represents the level of the independent variable, but the actual independent variable you don't see here. So it's not assigned in a column. The levels of the independent variable is assigned to the column. Do you agree?
Yes.
And if you follow that notion, then what are the values within the column then?
That's the dependent variable. That's the score which the participant achieved in that condition.
Yeah, exactly. So the actual cells that we have in the columns represent the dependent variable, and the column names on their own represent the levels of the independent variable. So this can be a bit confusing, because we were used to having the name of the column represent the thing it is, namely a dependent variable could be a column, and you would see the scores in the cells. But now we're in a situation where the column doesn't represent the independent variable. No, it represents just a level of that independent variable, and the actual cells within the column represent the dependent variable. So where do we find the independent variable now?
In the cells.
In the cells? Who agrees? Who doesn't agree? we find the dependent
maybe
variable.
say that.
We find the dependent variable in the cells, right? Not the independent variable. So the
What about the
actual
difference between them?
scores, the actual scores of the dependent variable you find in the cells. I interrupted you. Go ahead.
May I ask, like, what about the difference between them? Like, between the levels?
So we have level 1, no alcohol. We have level 2,
Yeah.
some alcohol. And we have level 3, much alcohol. So the thing I'm getting at is that within such design and within structuring your data this way, you don't see your independent variable. And even stronger, SPSS doesn't know what your independent variable is. So if I would name my independent variable alcohol use or drug use or whatever, that object, that thing called independent variable, it doesn't exist. So when you run this analysis, you have to tell SPSS what the name of your independent variable is and which columns are associated to the levels of that independent variable. Does that make sense?
Yeah.
Yeah?
Yes.
Very good. So it's and for this it's quite simple because we see our 3 levels of the independent variables, and we can imagine that there's an overarching independent variable which we can assign the levels to. But what we'll see later on is that when you do a factorial repeated measure, then it gets a bit more complicated to assign the right column to the right level that you want to test. But this is at least the way your data is structured in SPSS and that you use to run your analysis. So first off, we're going to look at the total variance explained. So again, this is nothing shocking. This is just looking at if we have all the scores, what is the mean of all the scores, and what is the deviation for each individual to that ground mean. So if you look at the data, if you would combine all the scores for all the 3 columns and for all the rows, and you would calculate the mean from that one, the mean sums of squares of the total variance that there is for each individual is compared to that ground mean. So the mean squares of the total, which is actually the variance, is composed of, again, of 2 parts, the sums of squares, and it's divided by the degrees of freedom. So for the sums of squares part, we'll be diving into this. But what we see here is, well, in R it's quite easy. We'll look at the total values and we just see what is the variance of the total value, and then we have what we're interested in. But for us, it's not really about what the actual value is of the variance, but more about what does the decomposition of that variance mean in terms of what parts are explained and what parts aren't explained. So the sums of squares is again, here we have it again, the variation, the variance of the ground mean multiplied by n-1, which is again not, it's a bit of an obtrusive way to write this down because you don't see really what's going on. I've applied it though. I've said, well, what is the mean squares of the total multiplied by the degrees of freedom? Well, that's 55 units of variance that are there to be explained. But what we could also realize is that this explained variance part is again the sum of what is the total, what are the individual values for each individual subtracted by the mean for all the individuals, the mean of all the scores for each individuals squared, which is the same. And this last way of notating what we're looking at will allow us also to look at this visually again. So what I've done here is again put all the participants on the x-axis and all the scores, the amount of accidents within the driving simulator, I've put on the y-axis, and the horizontal line is the grand mean, the total mean for all the individual scores that we have collected. So the total amount of variance that there is to explain is just the same as we've seen in all our previous example. It's the distance between the grand mean and the individual score squared, and we also square it for this score, and we've squared it for that score, and for this one, and for this one, and for all of them. So if we square all those distances and add them all together, then we end up with the sums of squares. Make sense?
Yes.
Yeah.
So it's no different than we've been doing all along. Now, what you can probably see is that the spacing of these dots are a bit different than I show usually, and that is because I've grouped them together. So what I'm gonna do is put some lines in between them, and what you see now is that I've put 3 scores within this these two vertical lines to indicate that this is one person. This is one person, this is the second person, and what we see is that within this one person we have 3 scores. We have the scores when the person had no alcohol, we have the scores when the person had a little bit of alcohol, and we had the scores when the person had a lot of alcohol. And we have that for each individual. So instead of every line representing a separate individual, now because we have a repeated measure, we have multiple observations per person, I group them together. Clear?
Yeah.
Yeah.
Good. So the next step, what I want to do is I want to know how much variance is there within the individuals. So if I would look at myself as dashing the 100-meter a few times, what my individual variation would be. Now I actually want to know what is the individual sums of squares, but for each individual. So if I want to know how much variance there is to explain within the individual, but for all those individuals, I need to find out what the relation is, or what the distance is between the scores and the individual mean. So the mean squares for the within factor, so the within individuals, is determined by the sums of square within divided by the degrees of freedom. So I could just calculate that quite easily and look at the degrees of freedom. So if I look into this sums of square of the within factor, I actually see the same kind of equation that we've seen earlier. We've seen that we're multiplying the variance within multiplying the variance with the degrees of freedom, n minus 1. But this is something, it's a different variance component because it's the variance component of I, and I refers to the fact that we are looking at the individual. So now we're actually saying, well, what is the variance within the person? And if we multiply that by the degrees of freedom, we're actually saying, well, then what is the sums of squares within that person? So I could calculate the variance for each person and multiply that by the degrees of freedom, where this n is denoted as an ni. So it's also the n for within the person. So what is this n? What's this value?
The number of measurements per person.
Exactly, and that was in our case 3. So applying this gives us the sums of squares, which is 48.45. Now, what I also want to do is, well, actually look at the difference between the scores of each individual and the mean within the individual. So instead of let's see this, instead of calculating the variance for the individual, you could also state, well, if I calculate the mean for each individual person, then I could also subtract that mean from the actual score of that person, and that is the variance components that we're actually interested in. So it's doing exactly the same thing, only it allows you to visualize in the next step what we're actually trying to look at. And it's going to be a piece of art at the end of this lecture, because we're going to have so much lines that it will be it will look pretty. So we have scores for each individual on the levels of the independent variable. We have a mean for this individual, and we could look at the difference between the mean for this individual and its actual score on the condition where he has a lot of alcohol. So you could look at that deviation, but you could also look at the deviation of the mean with the some alcohol condition and the mean compared to the no alcohol condition. And if you square these distances, add those 3, we will get 5.1, which is the sums of squares for that individual. And what you see is that for each individual you have different sums of squares. Some individuals have a lot of internal dispersion, and others have a bit smaller internal dispersion. For example, the second person here scores in all 3 of the conditions compared to their personal mean really close. So this is only 1.51. So we're going to look at this visually. So if we are looking at the mean of the individual, we have to add those. So what I've done here is, for each individual, I've plotted the individual mean as an orange horizontal line with the mean for this person, person 1. And I have the mean for the second person and the third person. It's also stated here what its personal mean is. And each and every one has their personal average. So if I want to know what the within sums of squares is, I look at the difference between this individual average and the actual score that this person had. If I square this orange vertical line and add it to the second and the third observation within this person, and I do that for the second person and all the persons together, then I have the sums of squares, the amount of variance that there is within the individuals. Does that make sense?
Yeah.
Okay, very good. So now the different parts. So if I want to know what between sums of squares is, I could actually try to calculate it and try to find those pieces of the puzzle. But I could also see that, well, if I have a total amount of variance that there is to explain. And I know how much variance there is explained within the individual. Then if I subtract those, I'm left with the sums of squares between the people. So you're actually looking at the between factor within this. So that will result in the sums of squares for the between factor. So it's actually looking how much variance do we have as a total, what part was explained by internal variation, and the thing that we're left over, that we were left with, is the between sums of squares for this group. But we're not there yet, because we're not really interested in this between factor. We are interested in what the difference is in the group averages across the three measurements, across the three repeated measurements. So we are looking at the essentially the mean squares of the model, and we've done all the previous steps to try to at some point, and you will see this, to try to determine how much we can reduce the amount of error in our total model to have a higher signal to noise ratio. So the mean squares of the model is again determined by the sums of squares. So now we're mainly interested in what are the sums of squares for this model, and well, it states model here and it states model in the book, but we're now actually looking at the group averages that we are interested in, much in the same way as we were with the independent variable independent ANOVA, or the one-way independent ANOVA. So what we see here is again a bit of a more familiar way to denote this. Well, we're looking at the group average and we're subtracting the total average. We're squaring those, and we are multiplying that by the amount of people that are in that group. And we sum over the amount of groups, the K, the amount of groups that we have. Well, we had 3 groups. We have repeated measures, and in our case, for every measure, we had the same people show up, so the sample size for each group is the same. So what we now want to find out is, well, what is the group average, and what is the deviation for that group average? So I first determined the sample size per group, well, which is actually the same for all. And in the final step, I will be looking at the mean for everybody in the non-alkyl group, and I will be subtracting the total mean and squaring this. I also do that for the some alkyl group and for the much alkyl group, which will result in the amount of sums of squares for each individual group. And those are 3. So if I have to sum these, I have to actually sum the 3 sums of squares part for each individual group. So here I'm telling R to sum over the first, the second, and the third level, which will result in 38 variance components that are explained by the being part of that group. And visually, this is totally in line with what we did earlier, but now I'm adding it, superimposing it on the rest of our data. So I told you this was going to be a piece of art. We have the green line, which is the average for the no alkyl condition. We have the red line, which is the average for the some alkyl condition, and finally we have the blue line, which is the average for the much alkyl condition. So in terms of sums of squares for the model, we're simply looking at the distance, the deviation of the group mean for the individual to the total mean, the black vertical line. And we're also doing that for the second person and for the third So if we're saying here that we're looking at the difference squared multiplied by the amount of people, well, we're saying, well, we're looking at the difference squared, the distance between this point and that point, multiplied by all the people we have. So it's 20 people. So it's this line plus that line, all the green vertical lines added together for our 20 people. That's the sums of squares for the first group. The second group we do the same, but then for the red line. So we're looking at the difference between the group average and the total mean. So for each and every one, this is the same distance. So we'll again multiply that by 20. And for the blue one, the high alcohol dose condition, we do the same. And that will result in the sums of squares for our model. Still following me?
Yes.
Okay, very good. Now we have the error part. Because, as I told you, we are trying to reduce the amount of error by with the fact that we have some information about how much variance is explained within each individual. So determining the error incorporates this. So we first have to, of course, calculate the degrees of freedom, and we have to find out what the sums of squares for the individuals are. And in the same line, we subtract our specific model that we found. So this is being part of the group. We subtract that from how much variance is there within the person. And the thing that is left, that is the sums of squares for the error. So we're reducing the error terms by adding the sums of squares within the individual. So this is a hard part to visualize, because what you're essentially saying is that you have to look at the differences between the groups and superimpose that starting from the mean of the individual means for each individual 3 times. So that will complicate things, but conceptually you can see here that if there's a part that is explained by the fact that I have internal variance, and if I take out the part that is determined by the fact that I'm part of a group, then you're left with the error of the total model, and that's what's happening here. So now I have the sums of squares for the model. I have the sums of squares for the error, which means that I could calculate the mean squares for both the model and the error. And that means that I'm essentially at the signal to noise ratio, because I have a part that is explained by the model. I have a part that is unexplained based on our complete model, where we add our within factor subjects, which will mean that which combined by its ratio, it's essentially giving us back an F value, which is the signal to noise ratio again. So if we do this final step, so what I've provided very early in the beginning here is that we do all these calculations. Let's see. Oh, this is a long list. Many steps. We do all these calculations, but we are actually only interested in the model. We're only interested if there's a group difference, but we have to filter out this within factor. So if you see the F ratio that is actually calculated, well, it's only for the model part and not for all the rest. So if I do that, we can, in our final step, calculate the F value. And yes, almost there. We now find that we have an F value of 74. Do you think that this is significant?
Yes.
Is there anyone who doesn't know if this is significant? It's pretty obvious, right? So the higher your F value, the more signal to noise there is. If you have an F value of 1, there's as much signal as there is noise. So an F value of 74 is off the charts with the amount of signal there is to noise ratio. But we'll test it again with using the visualize function, where of course you can't even see the p-value because it's so much to the right that it's not even visible. So what we're seeing here again is the probability of finding an F value higher or equal than this 74, which is 0.000000. Okay, I'll give up. It's very small. So we are rejecting our null hypothesis here, meaning that there is a difference between our alcohol use within the repeated measures. So the amount of accidents that we have differs in the no alcohol, a little bit of alcohol, and a much alcohol condition. Again, when we're going to run the analysis, we will have to find out where these differences actually are. Let's see in the final step, because what I've done here is just plotted the results using the visualize function, what I've also done here is added an alternative F distribution, and I have plotted what's showing here.
The critical value?
The critical value, yeah. Where do we find the critical value?
The green area.
The green area is the critical value. Is someone not in agreement, or?
Isn't the
I think it's around 3.
Oh, go ahead.
Go
I think
ahead.
it's just a number, probably around.
Yeah,
3.
so the critical value is a number on the x-axis, right? So it's the F value associated with it's the F value associated with a type 1 error of 5%. So it's not an area. Your critical value is not an area. Your critical value is a position on the y-axis. And your type 1 error, your alpha, that's a probability, and your probability is an area. So where do we find our alpha? What is it? In terms of this graph, can you point it out to me?
The green one?
Exactly. It's the green area. Why is it? What's your argumentation for this?
It's the area of the null that is
Yeah, it's under
it's the critical value or more extreme.
It's exactly, it's under the null distribution. And well, if it's 5% or not, is of course your choice. But we see that it's the area under the null distribution where it has a critical value, and we also see some orange area. And what's this orange area then?
Power.
Exactly. So it's under the alternative distribution, starting from the critical value that we find when applying an alpha of 5%. So the decision to the right is to reject the null. The decision to the left is to not reject the null. If we reject the null, what is the probability that is a wrong decision? The alpha. We want that to be low. And what is the probability that it's a good decision if this alternative distribution would be true? That's the power. We want that probability to be high, about 80%, mostly in psychology. Where do we find our p-value?
On the right side of the part.
On the right side, so I'll go to the right. Right. Yeah, here it is. It starts at 47. It's a blue area, but it's so flat and so much to the right that we can't even see it. But yeah, it's here, it's blue, and it's our p-value. And we see that our p-value in terms of area is way smaller than the area of the green that we have here. So that's what we see in this plot. I think it's time for a break. There was one question in the chat that I noticed is, do we have to be able to calculate these steps? Yes, you do have to be able to calculate these steps for the repeated measures, for the one-way repeated measures ANOVA. We need coffee. You too?
Yes.
Let's go get it. Yeah. See you in 10 minutes. Yeah. Welcome back. Got your drinks? Cheers. So we're continuing. Let's see. We've covered the interpretation of well the F value, but well, as stated, because we have three levels of our independent variable, we do not have well, actually information about what's going on. So to find out where the differences are exactly, you still have to well, either perform contrast analysis if you have a hypothesis on where the differences actually are, or again do the post hoc analysis to do all the multiple comparisons if you don't have any hypothesis and you're just looking at the at all the differences post hoc. So we've did that this before, and we've done this before, and we've seen that we can use both to find out where the differences are, and this is, well, for the repeated measures essentially the same, but as we will see when we go into the more complex models where we have the factorial repeated and the mixed designs ANOVAs, especially running the contrasts will make it difficult to interpret. So we have to look at this a bit more in detail when we run the actual analysis. So for now, well, of course you know that you still have to do this follow-up analysis, and finally, of course, we have to look at the effect size for your results. And essentially the same thing holds that we had in our previous analysis, where we said, well, you can look at some general effect size measures where R squared essentially represents the amount of variation, the total percentage of variations that is explained by the entire model, which is of course useful, but it's not telling you where the differences are, and that same holds a bit for the omega squared, which is only a general indication of effect size, but it still doesn't tell you which difference is larger and which is smaller. So for that, it's more convenient to look at the results for the contrasts or for the post hoc analysis, where we've looked previously at the results for the determining the effect size for the post hoc test, where we only had t values as results. So we just applied the same t-test calculation for getting to the effect size. But now within this model, within this analysis, you also have the option to use the f values for specific contrasts. And it looks a bit weird like this, but it's just telling you what is the f value for the residuals, and use that as an indication of the effect size. I see a lot of chat going on. Okay. So that is it for the effect size. What I want to do now is go into the factorial repeated ANOVA, and after that go into the mixed ANOVA, and there are no calculations anymore involved, so this was it, which is a lot already. But for this one there isn't, and we're just going to look at what is the setup, what does the data look like, and we're going to run it in SPSS to see how it works. So the most important part, and we've determined this already at the start of this lecture, that the factorial means that you have multiple independent variables, which could each and every one could have 2 or more levels associated with this, and each individual has to be tested repeatedly. So there's no independent variable involved here, it's only repeated measures. So what we're going to do is essentially the same type of study as we done with the previous one. The assumptions are the same, by the way, as the repeated ANOVA. But what we're here going to do is, instead of only looking at alcohol, we're gonna also look at speed. So we still want to determine the amount of accidents in our car driving simulator. But we now have 2 independent variables, one for speed use and one for alcohol use. And for both speed and both alcohol, we have 3 levels, namely no speed, going up to a little bit of speed, and a large amount of speed, small and large. Now the thing you have to realize is that because you're assigning each and every one individual to all conditions, you have to use all the combinations again. So I think we've seen this already with the factorial independent ANOVA. That's where you had a group of people that had to go into the specific category. Now you have one person that has to go through all. So you have to be in a condition where there's no speed and no alcohol. You have to go to the condition where there's no speed and a little bit of alcohol and a lot of alcohol. And all permutations that you have for these, you will have to have individuals go. So this is a simple representation of all the conditions that you have. So there are 9, and an individual person goes to the first one, the second one, the third, etc. So what you're also seeing is that in the naming of the variable here, I've specified that the variable name is indicated by essentially 2 numbers. The first one indicating the fact that the level for the first independent variable is 1, and the second is indicating that what the level is for the second independent variable. So this one, the first independent variable level is 2, and the second also, and here the level of the first independent variable is 3, and the second is 1. So what you're seeing here again is that the independent variable is not declared by the fact that you have columns. The values in the cells represent the dependent variable again, and the columns themselves, the naming of the column is, well, it is indicative for a level, but it's only indicative for the combination of the levels, the combination of speed and alcohol levels. So that means that if you want to run this analysis in SPSS, that you have to tell SPSS which variables, which columns are associated with which variable names. So you have to specify in SPSS that you have a speed variable as an independent variable, and you have to specify that you have an alcohol variable, and then you have to specify which level is associated with which, because otherwise SPSS just doesn't know what to compare. And that also means that you can do this in SPSS in a wrong way. So you have to be mindful of which column you're assigning to which category. But we'll dive into this in a second. So the data looks a bit like this. So you have no alcohol, a little bit of alcohol, and well, you can't see the entire name here, but you have 9 successive conditions that the participant goes to. So the first person first is in the condition no alcohol, no speed, and then he has a little bit of alcohol, no speed, and it goes up till you have all the 9 conditions. And I think I can't move these beyond this point, but maybe you can in the handout. So this is the structure of the data. So now let's look at this from an SPSS point of view. So we're switching to SPSS here, and what we have here is essentially again the same structure of the data. We have 9 consecutive measurements where we have in the cells the amount of accidents that a person has run into in the simulator, and we have a combination of the speed and alcohol conditions. So if you look at the variable view, you can see, for example, that we have here the variable 1, which is associated with no alcohol and no speed, well, I see it's still the Dutch geen alcohol, geen speed, so the G is for none, but it goes up from there. So still no alcohol, and then we get to the little bit of alcohol with no speed, little bit of alcohol, no speed, up until 3, a lot of alcohol, and fill speed, a lot of alcohol, a lot of speed. So this is what SPSS gives you in the data. Now, what do we need to do to get to this analysis? So again, I'm going to ask you to run me through this analysis. What do we have to do? Yeah, just call out. Where do I need to go?
You have to do analyses, general linear model, and univariate.
General linear model and then univariate. Everybody agrees?
No, 2 repeated measures.
2 repeated measures. So where do I need to go?
Repeated measures.
It's not just 2 repeated measures. It's the repeated measures within the general linear model. So we find that here. Very good. Well, together we'll get through this. Very good. So what's this? Anyone?
That's the alcohol or speed level.
Yeah, so the thing is, just as I told you, SPSS doesn't know that there exists an independent variable called speed and an independent variable called alcohol. So for SPSS to know that these variables exist, I have to specify them here. And that's what I'll do here. So I can create a speed independent variable, and I also have to specify the amount, the levels that this independent variable has. And we have 3, so I specify that we have 3 levels for the speed independent variable, and we also have an alcohol independent variable, which also has 3 levels. So if I add these, now SPSS knows at least that I want to look at 2 independent variables, each with 3 levels. Make sense?
Yes.
Yeah, very good. So I've seen this go wrong, where people just specify one with 9 levels, for example, and then you're saying, well, I just only have one independent variable with 9 levels. So that means that if you run such analysis, you only get results for, let's say, it's the same kind of analysis that you would run for the one-way independent, for a one-way repeated ANOVA. So if you do this, that would mean that you will get results on the main effects for speed, you will get results for the main effects of alcohol. And what more?
For the interaction.
Exactly, the interaction between the two, where of course you are a little bit interested in. You want to know what happens if there is an interaction between speed and alcohol. So we're specifying these here, and I've defined them, but we're not in the clear yet, because when we do, what we see here is that SPSS produces some, let's say, dummy variables. No, it's not really a dummy variable, but it's a placeholder. So it specifies that we have a within subject variable, and it recognizes the 2 independent variables that I just specified, namely speed and alcohol. Speed goes first, alcohol goes second. It realized that for each and every level of speed and alcohol, I have 3 levels. So what I'm seeing here is a placeholder coding, which indicates which variable should go here. So here should go the variable, the column that is associated with no speed, because it's the first level, and no alcohol. With no speed, a little bit of alcohol, going all the way down to a lot of speed and a lot of alcohol. Make sense?
Yes.
Yeah.
Good. So now I have to specify which one goes where. And I'm lucky here, because the way that I've defined the order of speed and alcohol actually corresponds, or does it? Let's see. What do you think? No, I'm just gonna shut up. You help me. Which one has to go where? We'll start with the first one.
The no alcohol and no speed condition.
So it's this one? Yeah. And then?
Doesn't it just correspond with the V1 and 2 that's written? So the no alcohol and a little bit of speed would be the 1 and 2.
1, 2. Yes, that's right. It says the geen alcohol, no alcohol, and a bit of speed. this is the second one here. But if you look at the order, no alcohol, a little bit of speed, it states here that it's speed and then alcohol. So I first have to find one that has the no level of speed and has a bit of alcohol. So it's not this one. It is, which one?
The third one.
The third one, exactly. So you see how you could do this wrong, right? You have to be mindful of that the values specified in SPSS also correspond correctly with the things you put in there. So it's this one, and then we have to have one which has no speed, geen speed, and a lot of alcohol. So that is this one. Can I combine that in one go? No, I can't. So this one has to go next. Then I have to have no speed and much alcohol. That's this one. Then I go for the next one. This one. 2 and 2, yeah. Do you still agree? Am I doing it correctly?
Yes.
Yeah.
Okay, so put this here and the final one here. And we're done. Now we've specified which column corresponds to what. If in the previous step I would have first specified alcohol and then speed, these two values would have been reversed and I would have a perfect fit. So the way you determine the variables can sometimes make it easy for you and sometimes a bit hard. But this is something to be mindful of, because if you're doing it wrong, you have the complete wrong interpretation of your results. So you have to be sharp and keen on this one, that you do this correctly.
Is it? Can I ask a question?
Of course. Go
Is
ahead.
it right to say that? So in the bit before this, where you were just putting in which variables you had, it doesn't matter which order you put them in as long as you code them in correctly in this step.
Exactly.
Okay.
Yeah.
Thank
But sometimes the assigning of the variables to the conditions is very easy, because if it exactly fits, you can just select all of them and just put them in. But if you have done it in reverse, then it's harder, of course. Okay. So the next steps are actually quite the same as we've done with the previous analysis. We just specify some contrasts if we want to do that. So that means here that we could say that for speed and alcohol we can run, for example, a repeated contrast. But I stated earlier that the Helmert contrast is actually the best one in terms of not violating the assumption of using more variance than there is. But then again, I told you, it doesn't always give an answer to the hypothesis that you have. I think Field specifies using the repeated for the repeated measures ANOVA, but I'm not sure. We could run some plots. So that means we could look at a couple of things. We could look at a plot for the main effect of speed. We could look at a plot for the main effect of alcohol. But we could also look at the interaction between speed and alcohol. And I'd like to see some error bars on this one as well. But we're doing a repeated measures. And that means that the error bars that are shown here are calculated based on the variables not being independent. So maybe it's better to not do the error bars, because they will be skewed. They will be bigger than they actually need to be. And there's a chapter in Field on how to correct your error bars for such analysis like these. Post hoc analysis we can do. But it's not working. Let's see. I'm clicking post hoc, but nothing is showing up. Okay, I'll skip it. Do we have some options left? Yeah, we wanted, of course, the descriptive statistics. We want to do a homogeneity test, and the reason SPSS calls this a homogeneity test is because it wants to test the equality of variance, the homogeneity, essentially. But the test it uses to do that can depend on the type of analysis that you're doing. So for this one, it will produce the sphericity test, but for the independent test, it uses the Levene's test. So it's a general term SPSS uses for these kinds of tests. And we'll stop at this. Okay, I'll run the analysis and let's see if this works. Okay. So I have the means, the standard deviations for each group here, which is useful to determine what's actually going on between the groups. And now we're getting at the first part, because what we're seeing here is you see a main effect for speed, a main effect for alcohol, and an interaction term. But this is pretty misleading that SPSS produces these results first, because what it states here is that you're looking at the multivariate tests. And we're not interested in multivariate tests, we want to do the univariate test. So the multivariate test was an alternative we could do if we would have violated assumptions. So what were those assumptions? Well, we had to have those equality of variance, and for that the Mauchly's test of sphericity was performed. So if we look at the results for the Mauchly's test of sphericity, for the three effects that we are interested in, namely the two main effects and the interaction effect, there should not be a difference between the deviations of all the levels that we have. So for speed we have level 1, 2 and 3. If we would calculate the difference between the first two and the second two and the last and the first, so all the combinations that are possible, this is what Mauchly's test of sphericity does for all of them put together, all the possible combinations, and then the test statistic is Mauchly's W, which essentially tests if there's a difference when the p-value is lower than 0.5, or there's no difference when the p-value is higher than 0.05. And in our case, for all three of the effects that we're interested in, we see that the p-value is higher than 0.05. So we are in the clear. So that's easy for us. But I think it's a good moment to step back to go back one bit into the beginning of our slides. Let's go up, because here we looked at, let's go up all the way. In the factorial repeated ANOVA, we looked at the, where was it? Oh, sorry, I had to go back up here. At the decisions that you could make if you violate these assumptions. So it's over here, yeah, this one. So what you're seeing here, that if your p-value is higher than 0.5, you just look at the sphericity assumed, so then you're in the clear. But if it's not, then you have to look at this epsilon value and see if it's lower or higher than 0.7. So looking at the results from your analysis here, it's about this epsilon value. Epsilon. So this value that you find here, if it's higher than 0.7, then you have different conclusions than when it's lower. So going back to the slides, well, if it's lower than 0.7 and your sample size is larger than the amount of categories that you have plus 10, then you would do the MANOVA. And with the MANOVA, so if you go through those steps and that is true, that would mean that in that case you would look at the multivariate analysis that is performed above here. So then you would look at the main effects for speed, alcohol, and the interaction in this table. But if it goes the other route, namely your epsilon value is higher than 0.7, then you can use the greenhouse Geyser value, and you use either that correction or the Heinfeld correction, and those corrections are found if you go here. So these are the actual results from your univariate tests, where your first one is, this one is for speed, where the first one is where sphericity is assumed, and then you have these kinds of corrections. So you have the greenhouse Geyser correction or the Heinfeld correction. So you look at these if you follow these steps. Now in our case, we just our assumptions are not violated, so we can just look at the sphericity assumed, and we see the main effect for speed in this row. So we see the found F statistics, we find the p-value associated with it, we find the main effect of alcohol and the p-value associated with it, and finally we see our interaction and the p-value associated with this. So in all three cases there is a significant effect, and to find out the direction of the effect you could either look at the means, or in our case we also asked for some plots, so we could also see what the direction of the plots is. Well, essentially more alcohol use means more accidents, more speed use means more accidents, and there is an interaction. So for the interaction part, you can see it here that combining a lot of speed a lot with a lot of alcohol produces more accidents, proportionally more accidents than when you only combine a little bit of speed or a little bit of alcohol or no alcohol with the high speed condition. So you see the lines are not doing exactly the same, indicating that there is an interaction here going on here. So the combination of speed and alcohol does something different for the high dose of alcohol than it does for the low dose or no dose of alcohol in these conditions. So that is what we're seeing here. If you want to test this these results, then we asked for some post hoc analysis, and we asked for some contrast. Well, the post hoc analysis are relatively straightforward, but the post hoc analysis are a bit difficult because it is applied also to the interaction term. So the table that I'm showing you here is essentially the contrast table. So let's zoom out just a little bit. So what we're seeing here is that for our first contrast, we suggested to do a repeated contrast. So for speed, what we're doing is we're comparing level 1 to level 2, and then in the second contrast, level 2 to level 3. So without regarding the level of alcohol, we can say that there's a difference between level 2 and level 3, between level 1 and level 2 for alcohol. And we're looking, yeah, we see a significant difference. And for level 3 of alcohol and level 2 of alcohol, these, we also see a difference. Still following me?
Yeah.
Okay. This is still relatively easy. Now for alcohol, we didn't specify that we wanted a repeated contrast. So repeated means comparing the first to the second and the second to the third, where you are actually using the second part 2 times. So that's a little bit of a violation, right? But when we're doing the Helmert contrast for the alcohol, we're comparing level 1 versus later of the alcohol condition. So we're comparing level 1 to the combined alcohol condition. So we've talked about this before, combining the two groups, the little bit of alcohol and a lot of alcohol use. We can see if there's a difference compared to no alcohol. And in this case, there is. And the later part, which is 2 and 3, level 2 and 3, then in the second contrast that you perform, you split these up. So you're now looking at level 2 versus level 3. And also here we find that there's a significant difference. All clear so far, right?
Can I ask a question?
Yeah.
How do you know which contrast we're supposed to use for each test?
This depends on your hypothesis that you have. So if you have a very specific hypothesis where you want to compare your baseline against alcohol use, then a Helmert contrast would fit very well, and then you could look at the difference between the 2 levels of alcohol use. But if you have a hypothesis that wants to know if a little bit of alcohol is if you have a hypothesis where you want to see if a little bit of alcohol is just as destructive as a lot of alcohol, well, then a Helmert doesn't fit that description because you're not testing that with the Helmert contrast.
I see.
Yeah.
Thank you.
So again, I won't ask exam questions where you have to be able to decide these kinds of questions to be able to perform your analysis. So I'll be very specific about what you need. But it's good to know that it all depends on the hypothesis that you have. So now it becomes a bit harder because what we're doing now is we're combining. We're doing the interaction term here, speed and alcohol. Can you see this? So you have speed and alcohol, where for speed in this column, you're looking at the difference between level 1 and level 2. But for alcohol, you're looking at level 1 versus later. And that one is significant. But what are you looking at? So level 1 versus 2 with speed, so it's the interaction graph. Level 1 versus 2 with speed, and level 1 of alcohol versus later means that you're actually looking at, let's say, an average of these 2 points put together, because you're combining those 2 levels of alcohol, and you're combining these 2 levels. Well, they're also almost the same. So you can imagine, well, this point stays around here, but this point, the average of this one and that one, will fall somewhere in the middle. So essentially what this is saying is there an interaction going on this piece of the puzzle. And that's just a little bit of a puzzle, because, well, we have that there, but in the next step you're looking at level 1 versus level 2 for speed again, but now level 2, level 3 versus alcohol. So that's also significant. So what are we looking at there? Well, we're looking at, again, level 1 versus 2 for speed, and then level 2 versus 3 for alcohol. So that's this point, this one, and the other one, but not the blue one. We're disregarding that. So only looking at those two parts. Is there an interaction going on there? Are there differences there? The answer is yes. So you have to practice with this. You have to see what the combinations are and how they relate to the results. And the thing here is to actually make such an interaction plot, because if you don't, it's very, very hard to see where the difference and what you're actually looking at. So we have finally the interaction level 2 versus 3 on speed, and then level 2 versus later for alcohol. Okay, so that one is then this versus that, and versus 1 for alcohol versus the combined of 2 and 3. So that's combining these two and combining these two. That's a bit hard, right?
You lost me as soon as it went into the
yeah. So you just have to when you're running the analysis in the weekly assignment, just try to dive into this and try to fiddle around for yourself to see what you're comparing with what, because you really have to spend some time to see what these comparisons actually are.
What does it mean if it's significant?
That there is some significant differences within those levels. So, for example, if you look at the last one, so that's comparing level 2 with 3 for alcohol for speed, and 2 and 3 for alcohol, that one is significant. So it states that for those combinations there is somewhere a significant difference. So that is 2 and 3 for speed and 2 and 3 for alcohol. So it's these 2 points and it's these 2 points. So somewhere there's a difference. Well, if you eyeball this, it's obviously that these don't really differ. This one could be a little bit bigger than that one, and this one is probably a bit higher than the other two. So your conclusion here would be that for the both high doses of speed, for the high doses of speed and the mid doses of speed, the amount of accidents when you increase the dose of speed goes up for both, but if you use a lot of alcohol, it goes up even more. So that would be in words something about this specific result for this contrast. So the highest number of accidents show when you use a lot of speed and a lot of alcohol, and they're comparatively higher than when you would have just a little bit of alcohol in combination with a lot of speed. Okay, we're going to go to the final step in our analysis, and that is running the mixed design ANOVA. And you're thinking like, well, we only have 5 minutes left. How can we do a complete new analysis in there? But it's no big step, because what the mixed design essentially does is the same analysis as we just did, but it adds an independent variable that is so it adds to the model an independent variable. So instead of doing just an independent variable as a repeated measure, you can add another or more independent variables with 2 or more levels as independent groups. So the assumptions still stay the same, and in terms of our example, we could do the same analysis, but this time we could add gender, males and females, to the model to see if there's also a three-way interaction between gender, speed, and alcohol. And the data, well, in the previous example, we didn't make a distinction between males and females, but now we do. So you have males in all these 9 conditions, and you also have females in all these 9 conditions. So the setup is the same. Our data essentially looks the same, but now we have another independent variable which is specified because it's independent and people are only uniquely categorized into one group. You now have a variable, independent variable as a column again, which indicates if you're males or if you're a male or a female. And in terms of analysis in SPSS, it would essentially say that you would have to run the same analysis, the repeated measures that we just did. Only this time you can add gender as an independent variable. And you run the complete analysis. And it's the same as we did before. Can you see what's even possible here within the mixed design? An extension to our models, an extension to our analysis that we haven't covered in this course up until now, and we're also not going to cover. But just looking at the dialogue, the window here.
You can add a covariate.
Exactly. So if you look at the dialogues of SPSS, you can see what's possible even more. So we could do a mixed design factorial ANOVA, where you correct for the covariates. So all these kinds of extensions are possible within SPSS if you wish to do so. We're not diving into those models in this course, but it's good to see and understand that these additions, extensions can be done. So the analysis would now essentially be the same. I just run the entire thing again. We still have the means, but now it's also split up for males and females. We have the multivariate results. We have the Maudsley's test of sphericity for speed, alcohol, and the interaction, because those are the repeated measures that we do. I think there's also a Levine's test in there to see if there's difference between the males and the females. We see no violations of our assumptions for equality of variance here. So we could again look at the main effect of speed, the interaction of speed with gender. We see the main effect of alcohol and the interaction with gender. We see the interaction of speed and alcohol on its own, which we already determined was significant. And we see the interaction of speed, alcohol, and gender. What is your conclusion based on the things that you're seeing now?
Gender doesn't make a difference?
Exactly. So what should you do when interpreting these results? Based on the sparsity principle, Occam's razor principle. You should throw gender out because it adds nothing of explained variance to your model. It has no interaction. It has no main effect. It's not relevant. So throw it out of your model. Stick with the main effects of speed and alcohol for people in general, without trying to split it up for gender, for males and females. Okay, that is it. All the ANOVAs that you can handle, right? I'll be sticking around for some questions, and I wish you the best of luck with the weekly assignment, and I'm still gonna see you two more times this week. See you then. Bye bye everyone.
Thank you. Bye.
You're
Bye.
welcome.
Thank you.
Thank you,
Bye.
brother.
Bye.
Hi, Sharon.